Good afternoon and welcome to the fourth lecture of our quantum computing course. We will start with a quick revision of what we did last week, and then we will go ahead with quantum theory. Last week we looked into systems to establish a mechanism of how we can have states and evolve these states over time that a system can be in. And we started with very simple systems, which are deterministic systems where we have a certain number of marbles, and we saw how we can represent this state as a vector, and then we can move around the marbles in various time clicks. And we described these dynamics in the system with a matrix, where the order of rows and columns is crucial. So the rows represent the individual position and the columns where the connections come from. So for example, here, this row would represent this position, and it has incoming edges from position 1 as well as from position 5. So the order is very important. And we discussed this, and we saw if we multiply the state from the right with the matrix, and then we can move one time click into the future. It's very important that we use column vectors for our states. However, we want to just save space, and we use a row vector, but then we transpose the row vector, so we're actually dealing with a column vector. We saw this, and we saw you can also multiply this transition matrix with itself, and then we would do 2 time clicks instead of 1 time click. Then we moved on to more complex systems, probabilistic systems, for which we said we only have one marble, and there are certain probabilities where we find this marble, that one marble in various positions, and eventually we store probabilities in our vector, and the entries in the vector must add up to 1. And this time we just have that one marble, so we deal with probabilities. And if we represent this dynamics as a matrix, as we see, for example, here, there's also a requirement that this matrix is a doubly stochastic matrix, meaning each row and every column must add up to 1. The dynamics is just the same. We can multiply the column vector from the right to do 1 time click into the future. However, we can also go into the past if we multiply our vector as a row vector from the left, and then we go 1 time click back. We saw if we transpose our matrix, we would also go back in time, and we looked at this time symmetry equation here to formalize this. It's again, we can multiply the matrix with itself to 2 time clicks and all of that. And we looked at a few examples like the stochastic billiard game and the stochastic or the probabilistic double slit experiment. Then we moved on to quantum systems, which are the systems that are of particular interest of this course. And these quantum systems, they work quite different. This time we don't deal with probabilities between 0 and 1, rather we deal with complex probabilities. And it's it's not a marble actually really anymore. It's probably just a much smaller particle, like a photon or something else, for which the laws of classic probabilities don't apply, but rather we deal with quantum mechanics. And why do we do this? Because if we can have an effect that we call interference, so probabilities can cancel each other out if we use complex probabilities rather than real probabilities. And this time we don't really know with a probability where that marble, or in this case, the subatomic particle would be, but rather what we have is we would have probabilities where we would measure that particle, because that one particle is in a superposition, so it is in multiple positions at a time. So we're not dealing with probabilities like before, but rather we deal with these complex probability amplitudes, and they don't mean that the particle is with a certain probability in a certain position. Rather, when we measure the particle, we have a certain probability to find that particle in that position. So this is far more advanced than the probabilistic systems. And this time, our state vector deals with complex probabilities, and there's also a constraint for this, that the sum of the modulus squared of the entries must be 1. And we looked at that. We looked at dynamics in quantum systems, and we saw also what unitary matrices are helpful for, because our system evolves, or our state gets multiplied with the transition matrix, and if we multiply from the left then the adjoint, then eventually this would undo the operation we had done before, which is something we'll exploit in computing when we talk about reversible computing. And we looked at a few examples of quantum systems. In particular, we saw the quantum billiard game, and the quantum double slit experiment is something we discussed in greater detail. And there we also noticed interference, so that our particle would actually never end up here, because these complex probabilities, they cancel each other out, and this is the interference. We discussed this in detail. We looked a bit into the double slit experiment, and that's something we will continue today. And we already introduced some important terms like a superposition, and then we also modeled composite systems, or we assembled systems, and we had smaller systems and aggregated them into bigger ones. And this is something we discussed in detail. And also these comments around vectors and matrices will be crucial to actually understand what each entry stands for. And we saw how we can assemble systems, how this impacts dynamics, which is actually some tedious process of multiplying these probabilities. We looked at assembling systems here from the perspective of probabilistic systems, but we can apply the same concepts to quantum systems. And rather than tediously trying to multiply the right probabilities, we can actually do this in a more formal way, and we use the tensor product for our two matrices to describe a composite system. And this was also your homework. You can think about how to complete this figure here in order to represent this transition matrix. We briefly talked about entanglement, and that's something we will continue today. How do you feel about last week's content? I know last week was a lot of stuff. We spent 3 hours on linear algebra, and later also complex linear algebra. Have you had some time for revision? Do you feel okay with the content? If so, send some positive reaction. If there are some doubts, maybe send a negative one. And if you have any doubts or questions, please ask. But overall, I only see positive responses. So today, or step by step, we're moving closer to computing. As of next week, we'll do computing and see how we can actually use all of these tools that we have so far to describe computations. And then later there will be algorithms, concrete quantum computers, and how we program them, as well as some theoretical foundations. But in order to better understand how to use the mechanisms we have established so far for computing, we will dive a little bit deeper into quantum theory today. We'll mainly see this from a probabilistic perspective. We won't be looking too much into the physics. For physics, we anyway have further reading in case you wish. This will all help us to understand some of these concepts we have already lightly introduced, like superpositions and states, in greater detail. And once we have done this, it will actually become much simpler as of next week when we build circuits and quantum circuits. We'll have much simpler states than the more generic ones we discussed today. Yet this will help us to understand some key concepts in quantum theory. So we'll be looking into states, superpositions, a bit into observables and measuring. We'll discuss dynamics again. We've seen this last week already, what unitary matrices are helpful for. We'll extend this a bit. We will also then assemble quantum systems. Last week, we assembled probabilistic systems, and today we will assemble quantum systems, go a bit deeper into this, and then discuss also in greater detail entanglement. That's something we had briefly mentioned last week. Um, Obviously, this is not a physics course, and we will not discuss quantum theory all semester, but rather we try to explain to exploit quantum theory for computational purposes. And why is quantum mechanics so interesting? We've mentioned it a few times in this course, and the book provides more details in case you want to learn a bit more about the foundations of quantum mechanics. Who of you actually had a look so far into the Quantum Computing for Computer Scientists book? I've mentioned the book since the first lecture. Maybe send me some signal whether you've had a look into the book or not. Um, if you have not looked into the book yet, it's certainly something you should be doing, and the book will turn out to be very helpful for your further reading and understanding what we are doing here. So last week we started discussing the double slit experiment, and the double slit experiment uh, is something super important to quantum theory. And we saw how these complex probabilities can cancel each other out. And today, one could see a figure here in which we will generalize this. So we have this light source here, because last week, we looked at that a bit simplified with the complex probabilities, and we saw we didn't have this continuous surface, but rather we had five of these targets. We had three targets here and then two further down here. And the target here is something that was shared by these two slits. And we saw that these probabilities would cancel each other out. And with the double slit experiment, you would see that if we look at the continuous surface here and not just at five discrete targets, and you have your light source here, and you have these two slits that behind here it's actually dark because these probabilities cancel each other out. And the book discusses the double slit experiment in detail. So if you want to learn more about it, please really look into the book because we have this interference here. So we have this canceling out. But in fact, if you close one of the slits, we don't have interference anymore. And you would actually have some light just here around the center, for which, when we use the double slit experiment, and both slits are open, we have this splitting, but then this interference. If we close one of the slits, this is actually not happening because there's no interference. So feel free to look into the book if you want to understand this double slit experiment in greater detail. And there's some additional text here, but I've mentioned most of this orally anyway. There's sometimes just some extra text for you for your further revision. Now, we will try to formalize quantum mechanics a little bit now, and we will see what quantum mechanical states look like, what they are made of, and how we can finally describe dynamics and superpositions in a much more, or in a somewhat more generic way than what we did last week. For that, I will switch to my whiteboard. So we'll look into states, and we'll have a state, and we look at this, we'll formalize this now more than what we used last week when we looked at some examples. And we will always have an n-dimensional complex column vector. So we'll have n entries, and this will look something like this. So we have n complex entries. We have Z0, C1 up to Cn minus 1. But just for also in the slides, to save some space, we will just use oftentimes a row vector that we transpose. So C0, C1 up to Cn minus 1. And that's transpose. So this is equivalent. And we will introduce a new notation now from now on. And what we will have is we will have a so-called ket notation, which is not an animal, but rather called KET. And these kets, they will look something like this. So when we have our vector, we'll have these individual entries, C0, C1 up to Cn minus 1. And what we think about is that a particle is at some point xi. So the particle being at that position xi will be denoted as xi ket. So we have this ket notation, and the ket refers to the left and the right end. And this is the so-called Dirac ket notation. It's actually from a bra ket notation, but we'll see the bras later. Don't worry too much about this symbol, but this simply comes from this bra ket notation. And when we have our n-dimensional vector, this one is actually composed of n basic states. So I think you remember from your introduction to linear algebra that you had in your first year, you remember the concept of a linear combination, right? Who of you feels okay with the concept of a linear combination? And so I see lots of positive responses. And we will now think about when we have our n-dimensional vector, how we can build it in terms of a linear combination of our complex probabilities and our basic states, because we have n many basic states. And all I'm showing you is also written in the slides, but I just find it more interesting to develop this now with you step by step. So we have n basic states. So we have an x0 ket, and the x0 ket would look something like we have a 1 in the first position, and then only zeros in the remaining positions. And these are all column vectors, but just to save space, I'll be using row vectors that I transpose. And then we have our x1, and we have a 1 in the next position, 0 here. And like this, we can continue up to our xn ket, or xn minus 1 ket, it's the last one, for which only the last entry is a 1. So we always have a 1 just in the next dimension. So first one, second one, up to last one. Now we have our vector here, and we try to build it as a linear combination of our complex entries as well as these basic states. So, and what we often do is now we also use this ket notation to refer to our state. So don't be confused too much about this ket notation. So we will have our state, and our state is often now called a psi ket. So we use a Greek symbol, and the psi ket is eventually a linear combination of our basic states as well as the complex entries. So we can see this. So we have a C0 times X0 cat plus C1 times X1 cat plus dot 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 up to the last entry. So we have our Cn minus 1 times xn minus 1 cat. And what you see here are these complex values, and these are just the ones we had before in our state. And these complex values are something we call now complex amplitudes. Or complex probability amplitudes. We look at this now from a very generic perspective. Next week, when we do quantum computing, we will actually only have these two here left because we have a 0 cat and a 1 cat, and the qubit, which is the fundamental entry, fundamental unit in a quantum computer. We have 0 and 1, and we're in parallel, so we have a superposition in both of them. But that's something we'll see next week. Today, we look at this from a much more generic perspective. But as of next week, it will get much simpler because we will only have a x0 and x1 when we look at qubits. So since our psi-cat is this linear combination, or it's a sum of products, and these products, we have the complex amplitudes multiplied with the basic states. So we could also say that eventually this is just another representation, C0, C1 up to Cn minus 1 transpose. So these are the complex amplitudes that we put in there. And we often now, or almost all the time now, we describe to a quantum state, we use this notation psi cat. And the cat are these two symbols here to the left and right. And this psi cat is a superposition, so also an important word that we looked at already in the past. And a superposition means that our particle is simultaneously in all of these locations, x0, x1, up to xn minus 1. So what we have is essentially a blend of all the xi's with certain complex probability amplitudes. So these complex amplitudes, they tell us precisely which superposition our particle is currently in. And this is totally different to our probabilistic systems, because there we had one marble, for example, that was with a certain probability in each position. Here we use quantum mechanics and we say that our particle is simultaneously in all the basic states. And it's not just that the particle is in one of them with a certain probability, but rather in all of them at the same time. But we also have these probabilities, and what are they now helpful for? So what we actually want is when we observe our particle, so when we do a so-called measurement, we want to know the probability of finding the particle in one of these positions, x0 up to xn minus 1. But this only happens after measurement. And what we want to compute is finally a probability p of xi. So what's the probability of finding the particle at a certain position after doing the measurement? And what we want is something like, we look at the complex amplitude Ci and take its modulus square. That's what we want to use to determine what's the probability of finding the particle at that point, xi, after doing measurement. But this may not be normalized. And if you remember from last week, we said that all of these modulus squared of the entries of our state, they need to add up to 1. But that may not be necessarily the case, so we need to normalize. And normalizing means we take our psi cat, and psi cat is a vector, and we take that vector's norm and square it. But because this now looks confusing, I use different colors to show you this. So we have our psi cat, which is our vector, and we take its norm and square it. So the norm is this one here, and the norm is in our case just the length of the vector. But norm and length, technically norm and length can be two different things, but here, because we take the 2 norm and we square it, this just means the length. Have you all heard the term norm before of a vector? So some positive responses. So because there are different norms, but here we just use the 2 norm and we square. I know there are other norms like 1 norm or infinity norm, but this doesn't matter here for this course. And then how do we calculate the norm? You remember this, we take the square root of a sum uh, in which we square each entry. So just formalize this a bit more, what we're doing up here. So the denominator can be calculated as something like that I have a sum, I have an index j, I go through the elements Cj, and I take their modulus squared, and I would sum all of this together. And then I take the square root, then I have the norm, and but I square the norm, and eventually here in green, I have a square root that I square, so it's just disappearing. Because remember, I don't just take the norm, but I square it. And that's why the square root will finally disappear. This is normalization, which is important to us. And last week we implicitly assumed that our states are normalized, but if they are not normalized, we need to normalize them. And that's what here in green, in orange is being done. It's the normalization so that our probabilities P of xi, they will always be in the following range. They are less than or equal to 1 and greater than or equal to 0. Because remember, we take here the modulus squared of the complex number, and eventually, because these are normalized amplitudes, eventually our P of xi will always be between 0 and 1, and all of these P of xi's will add up to 1. But this obviously only happens when you do an observation after having measured. And this observation is sometimes also visualized as the following. So when we say we have our psi cat is observed, it will always be observed in one of the basic states because our state is this linear combination of the basic states. And when we do such an observation, so after measurement, what is sometimes used in the literature is the following notation with such a wiggly line. And so our psi cat is observed in one of the basic states. So this would be the psi cat is observed in one of the xi cats. And because this is always one of the basic states. But this observation, that only means after measurement. Measurement is something we discuss in greater detail later. Are we all on the same page up to here? Maybe just confirm if this is something you got so far. Good. And now, with there only being positive responses, we can do an example. And test this together, that we all understood it. So we have an example. We have our scikit. We have 4 positions. So we have 4 points. So we have an x0, an x1, an x2, and an x3. And eventually our scikit has 4 entries. And as a concrete example, the first entry is -3 minus I, so that's the first complex amplitude, -2i, I, and 2. And maybe let's start with calculating the norm. So what I want is the norm of my scikit. And I'm just writing the scikit in blue so that we don't mix up the individual characters here or signs. So I want to know the norm, not the norm squared yet. This will come later. So this is one of the tasks you can test now without looking at the solution in the slides, obviously. You can try to calculate the norm of our scikit, and you have the individual 4 amplitudes in here. And once you have done this, we will actually try to do, then we will try to calculate one of these probabilities. This vector is not normalized yet. Later can also test the normalization, but what we have seen in here is we assume that our vectors are not necessarily normalized. So we normalize in here later when calculating this probability. But the probability will come in a moment. So what we calculate first is the norm here, which we need. So you can go ahead, and once you have the norm, let us know. I will develop this now step by step. So in case you don't know what to do, you can just see from what I'm doing. So the first entry is -3 minus I, and I want its modulus squared, because we set this down here. We take the modulus squared of the individual entries and sum them together. Then the next entry is -2i. We take the modulus squared, then an I modulus squared, and the 2 modulus squared. And I'll give you a short moment to think about how you could calculate these modulus squared. So this is largely now a revision or just a generalization of what we did before. So we have the first entry. What's the modulus squared of that entry? So the -3 minus I. You can share with us in the chat. So this is 10. That's correct. What's the modulus squared of the next one? So that -2i. What's the modulus squared? 4. That's correct. And the I is 1. And then another 4. So what we got here is the square root of 19, which is approximately 4.3589. So we have just calculated a norm of a complex vector. And what I want to know now is what's the probability of detecting the particle in x2 after measurement. So what I want to know is P of x2, And eventually, what I need to do is just this formula here. So I need to take the modulus squared of that specific entry and divide it by the squared norm. Modulus squared of this I, because I've highlighted this in blue, and divide it by the square root of 19, which is my norm squared. And if you got a solution for this, please share it with us in the chat. And the probability is something like, we got the right answer in the chat, 0.052663. So 1 divided by 19, because the modulus squared here of I is also just 1. So, as you can see, this is not too difficult overall. And the best thing we could do is obviously we deal with normalized states. And that's something we'll be assuming from now. But sometimes we will still see some states that are not normalized. And I'll show you now how to normalize the state or how to normalize states, and then we will move on. For this, just also for a revision or just for the proper visualization, we'll just quickly switch to my slides. If you've joined the course on iLearn, you anyway have access to the slides, but all I have shown you is these basic states, the linear combination. So our scikit is the superposition of the basic states. We've seen how to calculate this probability. I developed this with you step by step. We have this wiggly line for to denote the state of a quantum system before and after measurement. And the measurement is obviously then a classic value because when we do a measurement, our quantum system, that we have this terminology, we say it collapses, but we see this later. We've seen the state and how to calculate its norm. There are a few more rules that I won't be writing step by step here on the whiteboard, but rather we briefly look at that in the slides. So you can have two cats, like a psi cat and a psi prime cat, and obviously you can add them. So assuming they have the same dimension, and it's just vectors. It's just a different notation for a vector. So what we do is we have a C0 in our psi cat and a C0 prime in our psi prime. And the result is obviously we just sum together Z0 and C0 prime, and we do this for all the other entries as well, as you have learned for vectors. And here we're just dealing with vectors, we're just using a different notation. You're probably wondering why are these cats actually being used? Why don't we just write psi, for example? You will see in a moment there is a second part, the so-called pras, and pra and cats, they relate in some way, and then you'll see it's actually quite helpful to use this pra-cat notation. And we can also have a psi cat and multiply it with a scalar. The scalar can also be a complex value, and eventually we will just multiply it with each of the entries. As you know from regular linear algebra, also works here. You can also add a pra with itself. That's also fine. You can just multiply. You can just add xicat and psicat, which is just 2 times psicat in case you wish, and eventually each entry just doubles. And in here you see an overly lengthy derivation that eventually, when you multiply psi cat with 2, this will have no impact on these probabilities of where the particle is found after measurement, because you just double each entry, and eventually this will all just cancel out when you normalize. And this is shown here in a more formal way. So in other words, when we have our 2 times psi cat, we just describe the same physical system as psi, because we could replace this factor 2 with any other arbitrary complex number and still get the same results, because this constant factor would just cancel out when we normalize, because each entry just gets multiplied with the same complex number. And the length does not really matter as from a physical perspective, because for all the key operations, we anyway need to normalize. Like we've seen here, this normalization was done in this formula because we did not necessarily require that our vector is normalized. But how can we actually normalize a vector? And you can normalize a vector fairly easily. You've learned this also in linear algebra in your introduction. And normalization always means the length is 1 of your vector. And what you have done for real entries and vectors can be done exactly the same way for complex entries. So you have your cat, so a psi cat, and you just multiply the psi, sorry, you divide the psi cat by its norm, so by its length, and then each entry gets divided by that norm, which eventually leads to a situation in which your vector just has length or norm 1. I guess it's something you remember fairly easily from your introduction to linear algebra, and this also works with complex numbers. And when you have normalized, then this calculation of observing the particle after measurement becomes much simpler, because then you just take your entry Ci and take its modulus squared and you're done. When we assume that the vector is normalized, and then what will also happen is that each of these probabilities xi, so x0, x1, x2, they will all just add up to 1. And this is something that we also require for our, or it's something we will later see next week when we look at qubits, that we also require this for qubits, where we have a C0 and a C1 only, that their modulus squared add up to 1, because we expect them to be normalized. So as of next week, it will get much easier, because we will just have a C0 and a C1, and we will have much smaller states, in fact. So, and now you probably saw why we limited ourselves last week to normalized complex vectors, because it just makes a lot of these computations much easier. So last week we said we need normalized vectors. We didn't see how to normalize them. We just assumed that, or we require them to be normalized when we started, and they remained normalized by these matrices. And now you see why this is actually helpful, because then all of these calculations get much easier. We will do an example now, and for this I will switch back to my whiteboard. So normalization or normalized states. So we have a vector. So we have a psi cat for which we say the entries are 2 minus 3i and 1 plus 2i. It's obviously not normalized. And I want to see again from you, what's the norm of our psi cat? So it's just another practice this time just a norm, not the squared norm. And once you have an answer for the length or the norm of this vector, tell us. And once we have the length, we can just normalize. So I'll wait for you to send in the chat some suggestions what the length or the norm of this vector could be. The square root of something, and we have the entries 2 minus 3i modulo squared and 1 plus 2i modulo squared. So it's the square root of 18, which is correct, and this is approximately 4.2426. And now I want you to normalize this and maybe just don't work with the square root, but rather use some float numbers with a couple of digits and then tell us what the normalized vector would be. So normalized vector. So we would have our psi cat normalized. We can just call this psi 1 cat, for example. And if you have a suggestion for some numbers with a couple of decimals, tell us. You have a suggestion for the first entry as with a couple of decimals as a or real value, let us know. Be happy to see some numbers. Just use a calculator for this, obviously. So I have something like 0.41740 minus 0.70711i as one suggestion. And but it's there's probably a typo in here as I see. So should be 471 if I'm not mistaken. Guess there's a minor typo in the slides. And I'll fix that in the slides because I had these two flipped here. But the other one is correct. Then the next one would be something like 0.23570 plus 0.47140i, something like that. So this is one example of how we have a normalized psi now. And from then on, if you calculate these probabilities, Like here, you wouldn't need the denominator anymore, but just the numerator, because we have normalized vectors now. So, so as I said in a slide, there's a typo. I'll fix that until next, or I probably upload one slide deck at the end of the term that is fixed, and because overall typos are probably quite rare in here after having done this for a few years. However, if you see any typo, feel free to share it. So we've seen now what states are composed of, and now when it comes to our particles, they have a property, or our subatomic particles, they have a property that is called a spin. So what is a spin? Um, Spin will play a major role when it comes to actually implementing qubits, and particles, they can have a so-called up and a down spin. So we can have our psi cat, and it has a certain amplitude for an upspin as well as a downspin. And this is a property that can be used when we implement qubits in a real quantum computer, but that's something we see in a few weeks' time when we look at concrete architectures. If you wonder what the spin is exactly, there is the so-called Stern-Gerlach experiment, which was first performed 103 years ago. And there was a source of particles, like for example electrons, and there are two magnets, and with north and south, and then some particles they end up here, others there, and this was shown so along the z direction, and this is how, or was one of the first, or probably the first experiment to show the existence of this up and down spin. It's explained in greater detail in the book, in case you wish, but since we in this course mainly look at quantum theory from a probabilistic perspective, we don't care too much about the spin for now. The spin will be more interesting when we look at concrete architectures, and maybe for some of your seminar presentations, spin could be interesting as well when you look at concrete architectures. But this will come in a few weeks' time. And there are some examples here about the spins and how to normalize this in case you want to look at it for further reading. Now that we have studied our cats, we will study the second part of the bra-cat notation, which are the so-called bras. It's something you will see now. So remember, we had so bra cat notation. So we had our cat, so psi cat. And as there is a cat in this notation, there is also a bra, a psi bra. And these bras and cats, they relate to each other. And you will see in a moment that they are super helpful to describe certain transitions in a quantum system. And if I want a psi bra, the way I can get it is I take the psi cat and I calculate its adjoint. Remember our psi cat from before, so our psi cat was a column vector of entries C0, C1 up to Cn minus 1. Now, if I calculate its adjoint, that means I am taking the conjugate of each entry and I do a transpose. So my row vector, sorry, my column vector here becomes a row vector. And this is one of the few examples, we will see actual row vectors and not just transpose row vectors. So we take the conjugate of these complex numbers, C0 conjugate, C1 conjugate, up to Cn minus 1 conjugate, and it's actually a row vector. And let's do an example, just that we are all on the same page. I have a psi-ket, which are entries 3 and 1 minus 2i. And I want to know what's the psi bra. If you got a suggestion, please send it to the chat. And we got the right answer, almost the right answer by one sent it right, one still wrote a transpose, so there's no transpose this time. It's a real row vector. So the first entry is 3 and the other one is 1 plus 2i. And it stays a row vector, and it's not a transposed row vector. That's why I put the example here, just that we're all on the same page. Then I'll switch to the slides for the next part, just to tell you a little bit what this bracket notation is now helpful for. The example we just looked at is here, and what we will see now is that this bracket notation can help us to very efficient or very neatly calculate the so-called transition amplitudes, which you will see in a moment what this is. And eventually, when we use this bracket notation, we are calculating the inner product of that state space. And what does that mean? So the transition amplitudes, they will enable us to determine how likely the state of the system before a specific measurement, so the start state, will end in another one, the end state, after measurement has been carried out. So we start with a start state and then have an end state, and we want to know the transition amplitude of how likely this will happen to get from the start to the end state, and to observe this after the measurement has been carried out. And what we start with is a psi-ket, which is entry C0, C1 to Cn minus 1, and the C prime ket, which is C0 prime, C1 prime, up to Cn minus 1 prime. And we assume that they are normalized states. So this will severely simplify our calculations now. And what we calculate is the inner product. So we can extract the transition amplitude between these states. So from psi ket to psi prime ket, by doing the following. We say our psi-ket is the start state, and the end state will be a row vector for which its coordinate will be the complex conjugate of C prime ket. And what we calculate is here, we have our psi-ket and we have our C prime bra, and we just multiply them with each other. So the psi-ket is this part here, and our psi prime pra is this one here, because we take, and maybe I'll go back to the iPad to develop this slowly, so we actually see this step by step. guess this could be helpful if we build it step by step, and then it should be clear to everyone. So we have our SciCat, which are entries C0, C1 up to Cn minus 1. And we have the C prime cat, for which we have the entries C0 prime, C1 prime up to Cn minus 1 prime. And what I want to calculate now is from the right, my C cat, psi cat, and I want to multiply this with from the left with the psi prime bra. This is a slightly simplified notation. Sometimes this is also written just the same as the following. So I have my psi cat, and from the left, my psi prime bra. So this is the one component, this is the other one. But in this notation, if you just write them next to each other and you multiply them, it's often written like this. So we have one bar less, but it just means the same. So these two notations here, just the same, in case you wish. And now what we want to calculate is we need our C prime bra, because we have the C prime cat, and the bra would just be the row vector where we have a C0 and its conjugate, then the C1 conjugate up to Cn minus 1 conjugate. This would be, well, I'll use a different color. So this is this one. Then from the right, we multiply the column vector, which is our C cat, psi cat, C0, C1 up to Cn minus 1. So this is this part. And what we do is we have a row vector on the left and a column vector on the right. So we just multiply this element-wise. So the C0 with, and I should probably still add these primes because it comes from the psi prime. So I multiply the C0 with the conjugate of C0 prime and so forth. And finally, I just get a product. So I can just write this out. It's the C0 prime conjugate times the C0. This is a first product. Then the C1 prime conjugate times C1 up to Cn minus 1 prime conjugate times Cn minus 1. Are you okay with this one here? Maybe just send me a signal if you got this. Looks good. So it seemed to be helpful to develop this here step by step with you in live rather than looking at it in the slide. And so we've done this here. And what it means is, so this inner product here gives us this transition amplitude that we have a state transition from the start state to an ending state. And this transition amplitude, so from psi to from psi cat to psi prime cat, to calculate the state transition amplitude, we take here the inner product of these two. So can be described fairly easy with this bra cat notation. And it allows us to shift the focus from states to state transitions. It's just a different approach of what we had actually done before, but here it really helps us to get to focus from or shift from states to state transitions. There are a few extra notes to pay attention to. It could happen that this transition amplitude between two states, it can be zero. And as you know, if you take this inner product of two vectors and the inner product is zero, this means here that this transition amplitude is zero, so that they are orthogonal to each other. So two vectors are orthogonal, and then the inner product is zero. From a physical perspective, this would mean that they could be seen as mutually exclusive alternatives. So an electron can be in some arbitrary superposition, for example, of spin up and down, but after we measure it in the z direction, it will always be either up or down, never both at the same time. And what we need from now is, you've seen this also in your introduction to linear algebra, when we build our linear combinations, we need a basis, so we need basis states, and these basis states, they need to be orthonormal, and orthonormal means, anyone remembers the term orthonormal from the introduction to linear algebra? Give me a signal if this is something you remember or not. So in an orthonormal basis, all the basis vectors are mutually exclusive. So they are all orthogonal to each other. And that's exactly what we also built here in the beginning, when we, the very beginning today, introduced our basis states, which were these ones here. They are all orthogonal to each other, and that means the basis is called so-called orthonormal. But some of you said they remember this from the introduction to linear algebra. Obviously, you can have other bases than the ones we had so far. And maybe in your linear algebra course, you have also learned how to convert from one basis to another, but this is not too important today. And just again, from a generic perspective, our psi ket can be in a certain basis. The basis so far we assumed are just probably the most simple basis we had, but you could have a different basis as well. And eventually you have these basis vectors, b0, b1 up to bn minus 1. And we build our psi ket as a linear combination using these basis vectors and the corresponding complex amplitudes. And we would also assume that these complex amplitudes, they're eventually these transition probabilities of bi and psi, and that the modulus squares add up to 1. So it's just a generalization of what we discussed actually the whole time, which could be interesting for your revision. And eventually, we have our state psi ket, and when we measure it, the quantum state, which is a superposition of these basis states, will collapse into one of them. And this measurement is something we will see again later in greater detail. The measurement is also non-deterministic. So if I have a quantum state, and I may have a very large transition probability, say for example, this one here, and I measure, after measurement, I may find the particle most likely in B0, but if I run the experiment again, I may get a different outcome. So that also adds uncertainty when we see computations next week. So this quantum state will collapse when I measure, and it will collapse into one of these classic states. Not always the same one. But the measurement, if I do it, the quantum state is gone and I'm unable just to go back and recreate the quantum state. But then I have one of these classic states. But we'll see this again when we do measurements and when we do real computations. Now, what we just did is, so we calculate these amplitudes of the transitions. And just to make sure we have actually fully understood it, I think it's good if we add one more example and calculate this. So, example. So we have our cat, which are two entries, 1 and I. But because this is not normalized, we need to normalize them. So we could say 1 divided by the square root of 2. That's actually normalized, but sometimes in the literature, this is written as square root of 2 divided by 2, which is just the same. But sometimes in some notations, it's preferred to put the square root in the numerator rather than the denominator. It's the same result eventually. And then we have a phi cat, so a different Greek symbol. And this one is I and -1, and it's also normalized. And now what I want us to, or what I want you to compute eventually is the inner product. So we have our cat, and from the right and from the left, the phi bra. I want you to calculate this, but in order for this to work out, I first need the phi bra, because I only have the phi cat. So this will be a row vector. It's -I and 1. The normalizer just stays as before. So, and now it's your task to calculate this one here. And if you have the result, share it with us in the chat, please. There's a question about one result. What you have will be just one scalar value eventually, not a vector. And sorry, I made a mistake. I think that's what you meant. Yes, that's obviously correct. It's a -1 here, which was already there. Yes. So just missed the -1. It's correct in the slides, but it's a live demo. So sometimes mistakes happen. So if you got a solution, maybe share it with us. We got the right answer in the chat. The answer is -I. So don't forget, obviously, these normalizers. I've just moved these normalizers out of the vectors, but they apply to each entry. So the result is -I. And remember, for these transition amplitudes, you can have this bracket either written like this or like this, where we actually highlight more the cat and the bra, so we only have one bar. Or what we are calculating is just the inner product, and the inner product is sometimes written like this, with the phi, comma psi. So these are all just equivalent ways to denote this than up there. It all just means the same based on where you look at the literature. You see either the first one, the second one, or the third one. This worked fairly easy because the states are normalized. One could think now, what if our states are not normalized? So when it's not normalized, then imagine we just use the same vectors as before, but unnormalized. So psi, which is 1, and -I without, oh, and, or we just, I'm just seeing which ones we use, or just use the example from the slides. And yeah, we just use the example from the slides, slightly different to this one here, but just use different ones. But eventually, it doesn't make a huge difference. So we use the psi cat and the phi cat, and this one here would be I and 1. So before this was 1 and I and -1. This time it's 1 and -I and I -1. And if you calculate this, say you can, if you take the inner product, so we need the phi bra, which is -I and 1. When we calculate this inner product, so phi and psi, you would get like -2i, and because they are unnormalized, I need to normalize the product. I just got a question here from one student about this one here. Just if you don't get the result, just try it out step by step. And my advice is you just move these constant factors into each element, and then you will see that the result is -I. So don't forget these constant factors. And for this one here, we used unnormalized vectors, and the result is -2i. So I would still need to actually normalize the result. And there's an equation for how to do this. So if you want to use unnormalized states, the result, how to get the correct transition amplitudes, would be in the numerator, just as before, our phi and psi. So what we have just done, but you need to divide by the product of the two norms. So I put them in blue, these norms. So the phi cat and the psi cat. And I want to calculate the norm of each of it and then have the product of these two norms. And this would lead to a normalization of the result. assuming we have used unnormalized states. And if you apply this equation to here, so we have just calculated the numerator, you would still do this for the denominator, then you will see that this is fairly easy because we have the norm of our phi cat, and the norm is just the square root of 2 because we have an I and a 1. We have the norm of the psi, so norm of the psi cat would also be 2. So what would happen here is we have our minus 2i, and we would multiply it by the product of square root 2 and square root 2, which is, we would divide it by the product of them. So the product is 2. So minus 2i divided by 2 is just minus I eventually. We have also detailed this in the slides in case you wish to follow this step by step, or you would normalize them first and see you would get the same result. We will now briefly look at two topics, which are observables and measurements. We will just discuss them briefly because as of next week, we'll do computing, and then we don't need observables and measurements from a highly generic perspective. Yet I quickly want to tell you what's behind these terms. And physics is generally about observations. Like in traditional physics, classic physics, we have quantities like mass, momentum, velocity, and so forth. And they only make sense if we can observe them in a quantifiable way. Now, when it comes to quantum mechanics, we also have a set of observables, so physical quantities that can be observed in each state of the state space. And this can be described with so-called observables, and we will just quickly go through this because next week, when we look at quantum computing, we don't know it, we don't need this from that generic perspective. So there's an example here in the slides and in the book how to observe. So we would have a two-dimensional spin state space and what you can observe from it. And um, if you want to see this in detail, feel free to look at it. And what is also important in that context is then the reduced Planck constant. But this is something that would probably be more interesting to physicists. So the reduced Planck constant is called h bar, written in this way. But we don't want to observe too many different or not that many different things when we do quantum computing because we just deal with much simpler state spaces, which are just 0 and 1. So if you want to study this in detail and the Heisenberg uncertainty principle, feel free to look into the book. But it's largely interesting for physicists, and they actually spend a lot of time on this around quantum computing. But we as computer scientists, we're actually interested in something else. What is more important for us is later to do measurements. So we need to measure, so we have later a quantum state, and we need to measure if finally that quantum state collapses into a 0 or 1. Because when we start a quantum experiment, we put some classical values in, we initialize the qubits with classical values, then we create a superposition. How to do all of this from a computational perspective will be covered next week. But then we have our quantum system and we do operations, and eventually we need classic results, which are 0 and 1. And for that, we need to do a measurement on the qubit. And again, in quantum computing, this will be largely simplified because we just deal with zeros and ones. But when you do measurements on more generic quantum states, this becomes more complex. And it's actually related to the concept of observables. And something you will see is that our quantum system will always collapse from some state to some eigenvector of the observable. But as of next week, we don't need all of that in that detail because we just deal with zeros and ones, and then we don't have that many eigenvectors. In fact, we can just collapse to the one basis vector or the other basis vector. That's why I'm skipping the details of observables and measurements. However, if you care about this or you want to get some extra insights, feel free to look into the book, which covers this quite in greater detail. What is now more interesting for us is the dynamics, because we will have a quantum state. We apply some operation in a quantum computer to it. It evolves into a new state. And then we apply operations over and over. But at some point, and you will see this when we look in quantum computing, we need to be able to undo some of these operations. And that's something we already touched a little bit last week when we looked at unitary matrices. And this is something I want to extend on now with you. And we'll look at that and look at multiple unitary matrices. So imagine dynamics. We have some state psi at a specific point in time. So at time t. And I will multiply it with a unitary matrix U. So our psi cat will have evolved into the future. So we have a psi cat of t plus 1. Because we had the state, we did some operation in a quantum computer. This U, a unitary matrix, will always represent some operation, some fundamental operation. We see as of next week, which ones actually exist in a quantum computer. And then we apply operations over and over again. But later, we want to be able to undo some of these operations. And for that, we need to work with these unitary matrices in the right order. So this was the general idea. And now we can look at multiple unitary matrices, different operations to make this happen. So we have our psi cat that we are starting with. And we are applying some matrix now, some matrix at point, say, U1. And so we had our start state, psi, and multiplied it with U1, which is, I just still use the red one, and it becomes easier to understand. This is some state now, and I'm applying a different operation to the state now. And we can denote this as, so we had our psi cat with our U1, and we always multiply from the left, as you saw from last week, or as you saw last week. And then we have another gate, some other fundamental operation in a quantum computer. Now we have a new state, and this will be psi cat U1, U2, and U3. And this is some state now, and I've just written it out that we have still these matrices here because U1, U2, U3 are unitary matrices. And in a traditional computer, for example, you have two variables or two registers, you add them, you subtract them, you multiply them, you're evolving. But with quantum computing, we can actually undo some of these operations because as we progress, we create new states. But what also happens is sometimes, and you'll see this as of next week, we will create unnecessary superpositions. Because sometimes we have one gate, but we need another one that needs to be used with that one for various reasons, as you will see. But this creates sometimes unnecessary superpositions because more gates may sometimes mean more superpositions, more qubits needed, and therefore more superpositions. And sometimes I need to evolve like this, but once I have done some specific operation, I want to undo a different one I had to do in order to get there, and I want to reduce the superpositions now. You'll see this next week when we see quantum circuits. Now, say I have this state here that has evolved, and I want to undo one operation. Which is the operation, which is the only operation I can undo at the moment? Do you have any guess if I multiply from the left with the adjoint matrix, which is the one I can use here at this moment, or which operation is the one I can actually undo here at the moment? If you have any guess, or they got the right one, it's U3. This is the only one I'm unable to do. Because what I have is I have my U3 and it's adjoint, so we can write this out in detail. Because what I have here is, so just as a note, what I would have is my psi cat, my U1, my U2, the U3, and the U3 dagger, the adjoint. And these two here, by definition, this would become the identity matrix, because that's what we require from unitary matrices. And so far, all the matrices we use here have to be unitary. Now I have undone one operation. And I'm now at this state here again. So I just went back. This is called reversible computing. It's something that we can do in quantum computing with all operations. With traditional computers or binary computers, at least most of the operations we use, they are not reversible. If you add two numbers, you cannot just reverse this. We can reverse a not, for example, or a change of sign plus minus, but just an addition or an or an and cannot just be undone. Now I want to undo another operation. So I went once back, which is now the operation, the only one I'm able to undo. As the next one, you can send this to the chat. This is U2, that's correct. So U2 dagger. And then the last one I could undo is the U1, so U1 dagger. And this has to happen in exactly that order. And you'll see this next week when we build quantum circuits. For example, if you have something like what will not work, could be something like this. So I have my psi cat, just as before, the U1, U2, and the U3. I cannot just suddenly undo U1 by putting my U1 dagger. Obviously, it's a valid operation to multiply this here with U1 dagger, but it will not undo the operation. Rather, it will evolve to some other state because these matrix multiplications, they are not commutative in general. So not commutative. That's very important And that's why doing something like this here will not just undo my U1. It's basic linear algebra, but I still wanted to mention it here. So these dynamics are also explained in greater detail in the course book in case you wish to read about this, but I guess we've already looked at this now in quite some detail. And we will emphasize on these dynamics further in the course, especially next week. Now, I'll switch back to my slides. This is what I've just shown you. I've also shown you this. I just wrote the U1, U2 slightly differently, but this is a screenshot from the book. And you can read more in chapter 4.4 if you wish. Last week, we started assembling systems and we used probabilistic systems that we assembled. And today we will assemble quantum systems and observe some very strange effects that we had not observed when we assembled probabilistic systems. So remember, assembling systems meant we have multiple systems and we want to compose them into one big one. The motivation for computing is because in computing, we will have multiple qubits and we want to have gates that work on multiple qubits. And each qubit could be seen as a system, so we somehow need to assemble them to run operations on multiple qubits at a time. So we need to know how to assemble quantum systems. And say we have two independent quantum systems, Q and Q prime, and they have their vector spaces V and V prime. And if we want to have this quantum system by merging Q and Q prime, what we need is the tensor product of V and V prime. And this will be the new state space. This is actually just more generalized than what we discussed last week when we started assembling systems, but it isn't actually different. It's just a bit of a more generic explanation. And very importantly, we can do more than just assembling two systems. We can have many systems, so the tensor product of vector spaces is actually associative, so we can progressively build larger and larger systems. And if you imagine now this would be the one qubit and the other qubit and so forth, we actually want to be able to combine more than two qubits if necessary. And it's something we will need, as you see, next week. Now, we will again develop this next piece step by step. Imagine I have one system. So the headline is Assembling Quantum Systems. So system one has n basic states, and system two has m basic states. So how many possible basic states does the assembled system have? So you can send in the chat how many basic states the assembled system would have. If I have n in the system one and m many in the other system. So very important, not at, but the product. We've seen this with an example last week. Now we will formalize it. So the assembled system is n times m basic states. And we can discuss now a little bit some notations and some examples and see what this actually means, because then we will observe some very strange phenomena that can happen in such assembled quantum systems. Imagine we have x0 cat and the tensor product of this with y0 cat. So the x comes from system 1, the y from system 2. And what this one here means is the tensor product of x0 and y0 means the first particle is at x0 and the second particle is at y0. Just as one example. We could have something like x1 cat and the tensor product with y0 cat. This would mean the first particle is at x1 and the second particle at y0. Again, we can generalize this and we can say xi, tensor product with yi. This means the first particle is then found at position xi and the second particle at position y. Maybe not I, but let's should be actually a J, not an I, because it's independent indexes. So this is a J, probably just to write it better. So J, Xi and Y, J, meaning the first particle is found at position Xi and the second particle at position Y, J. We can look at an example now what this means, and then step by step we will get to some very interesting effect that we get to notice in such systems. We assume n is the same as m, it's 2. So we are dealing with a state space with 4 basis vectors, so it's complex numbers. We have 4 basic states in this state space, where n and m is 2, so 2 times 2 is 4. So the standard basis of such a system is a set of our basis vectors. So the first basic vector is the tensor product of x0 and y0. So this is the first basis vector. So this is first basic vector. And the basic vector here, in that sense, is a tensor product. Then x0 and the tensor product with y1. This is the next entry. Then x1 cat and y0 cat. And the third entry would be x1 cat and the tensor product with, and I've just noticed the screen share stopped for some reason. We'll be back very soon. And y1. So the first basis, then the second basis, and then the third basis. So 4 basic vectors in the basis. And we can generalize this for 2 states and or for 2 systems. We can say, so from a generic perspective, that our psi cat, which is now from a composite system, is a vector in the m times n dimensional complex space c to the power of n times m. So if n many basic states in the one system and m many in the other, so psi is a vector in this m times n many dimensional complex space. And we can write this out and we can say our psi cat is, so we write down these basic vectors. So we saw our x0, the tensor product with y0, then dot, dot, dot. Then xi, tensor product with yj. And then again, dot, up to, we have our xn minus 1 cat with the tensor product of ym minus 1 cat. So this is, we start with the zeros, then indexes I and j up to n minus 1 and m minus 1. Are you all with me up to here? That maybe just confirm with a thumbs up or thumbs down if this makes sense, that we have generalized the basic states like this. And what's missing now when I have my psi, which is a superposition of these basic states, what's missing at this point? Because I have the basic states. What else do I need for the superposition or for the linear combination? Maybe let us know in the chat what you think, if anything is missing, and if so, what is missing? This isn't too different to the single systems before, because we had the basic vectors and we need something else. If I shall wait for anyone's answer in the chat, maybe just send me a thumbs up. If you don't know what could be missing here, maybe send me a thumbs up or a red sticker or something. Okay, we can go back to earlier today when we looked at the superpositions. We had the basic states and we had the amplitudes. So now when we look at an assembled system, we also need amplitudes. And one person also wrote this in the chat. So I need amplitudes, but this time I should not just call them C0, but rather C0, 0 for both indexes, for I and j. So Ci, j, and C n minus 1 comma m minus 1. So this would be a good way for the terminology. And then I have these complex amplitudes, and eventually, if I have something like Ci j modulo squared, this would give us the probability of finding the two particles at positions xi and yj respectively. After measurement, obviously. So we had this before for a single system, and now we have a composite system, and all we have is maybe different basic vectors, which are the ones in green, and I have my complex amplitudes. But it doesn't look that much more sophisticated. It's just other basic vectors, which are the tensor products of the basic vectors from the single systems, and I have some complex amplitudes now. How to calculate these complex amplitudes, that's a different topic. But eventually, this is just a highly generic description. And obviously, you could extend that. So we could extend that with maybe, another tensor product of a third system. So maybe a Z0 if we wished, but that's just an extension. So extension to third system. And then we would need probably another index as well. So this not only works for 2, but also for 3. Is this now more clear to you? Maybe let me know if this helped. So we see what all of the components mean. If you feel you got better now what this structure means, send some signals. I'm already getting some first thumbs up. And ideally, these probabilities should be normalized, which they may be or they may be not. And we can look at an example now. So we can say our psi cat is the following. I'm just writing down, first of all, the basic vectors. So the tensor product of y0 and y0, sorry, x0 and y0, then x0 and y1. And we just assume that n and m is 2. So we have 4 components. So x1 and y0 and x1 and y1. And now I need to put here the probability amplitudes. So here we say the probability amplitude is 1. Here we say 1, sorry, it's I. I is the first one, then 1 minus I, and then a 2, then minus 1 minus I. And so I, 1 minus I, 2, minus 1 minus I. Do you think this is normalized complex amplitudes? If you think it's normalized, maybe send a thumbs up. If you think it's not normalized, thumbs down. So maybe some more answers. Thumbs up means you think these amplitudes are normalized. Thumbs down means not normalized. So this is definitely not normalized, because if this was normalized, then the modulus squared of these 4 entries, so each modulus squared, and you add them up, this would need to be 1. And obviously it's not normalized. So your intuition was correct. So this all just looks more complex than it is, but in fact, I simply have different basic vectors. That's all. And I have more basic vectors than before, but the rules are still the same as before. And now I have a question. What is the probability of finding the first particle at position x1 and the second one at position y1 after measurement, obviously? So what's the probability that I find the first particle in x1 and the other one in y1? So I want to calculate this probability. So remember from before, we calculated already all of this for single systems, and now we simply have accurate or composite systems where we did something like this here. You remember we did this one here, and it worked for a single system, and obviously it works for composite systems as well. What is key is the numerator, and if the amplitudes are not normalized, I need the denominator. So here I need the denominator too. But all I need is to pick the corresponding probability or complex amplitude here. And that's what I'm doing now for my composite system. So x1 and y1, that means I need to look at this one here. And I need its modulus squared. So the modulus here is -1 minus I. Square the modulus. It's just the same equation as before. And if the system was normalized, or if the vector was normalized, I would be fine. So in the vector, I have these blue entries, but it's not normalized. So I need to normalize the result. That means I sum up the modulus squared. Or we said before, we square the norm of the vector. But squaring the norm just means the square root disappears, or I just say it's the sum of the modulus squared of each entry. So modulus squared of I, then 1 minus I, then 2, and -1 minus I. And this will, in fact, lead to something like 0.222, whatever. And again, I could do this if I wished for a third position as well, if I wanted. I would just need to have, obviously, a different vector with different amplitudes. But this is something that not only works for two systems, but for multiple systems. Maybe just confirm if this makes sense now to you. And if you're confused, maybe send a different reaction, send a negative one. I know it's not easy. But finally, all these formula from today, we can just extend it to multiple systems. And it isn't that difficult, in fact. And we will need such stuff next week when we have multiple qubits. And actually, we will have a lot of qubits that we assemble, not just two, but many. So this will all look even more complex. That's why we're building it step by step. But for each qubit, we only have two basic vectors, so it doesn't get that bad. Now, we have done the assembling. Now we will come to something that is called entanglement. And I'll show you this. But before we look at entanglement, I'm just briefly recording my slides for those who don't have access to my slides. We looked at the tensor product when we assembled the quantum system. We saw we had two small systems, then we had four basic vectors. We looked at this generic state vector for two systems or two states into one big one. And we looked at that example where we find these particles in these location in system 1 and system 2 after measurement. So this always means after measurement, but I said this before today already, and I'm not writing always in the slides after measurement, but we can only find the particle once we actually have done the measurement, which collapses the quantum state. Now we get to the last topic for today, entanglement. And now we've seen we can build more complex systems and describe more complex states as this aggregate of multiple systems. And entanglement will show us something very strange, as we will see very soon. Imagine, so we've seen we have the basic states of the assembled systems are just the tensor product of the basic states of the single systems. Now, it would be really cool, and I'm highlighting this here, if each generic state vector could be just written as the tensor product of the two states. So one part comes from one system and the other part from the second system. So, and we would think that this would always be the case because we have these two systems, and that the generic state vector could simply be written under all circumstances always as the tensor product of the two states. Is this something you would also assume would be really cool and probably be possible? Just from naive thinking. If you think, well, I have two of them, now I have the tensor product, so all the generic state vector can be written always as the tensor product. If you think so, yes, maybe thumbs up. If you think that's not the case, maybe thumbs down. And if you think that this is possible, yes, thumbs up, perfectly fine, what you would think, but it turns out that this is not true. We will be able to have states, so-called entangled states, which we cannot describe using the tensor product of the individual systems. And this is something I will also develop with you now. The iPad will be online soon. I just need to plug in the iPad because somehow the battery is dropping quite quickly because we've been doing math for a few hours. So, entanglement. We can think now about one state, psi cat, and it actually only has two components. We have the x0 cat and the tensor product with y0 cat plus the x1 cat and the tensor product with y1 cat. So very simple psi cat, as we think simple, but in fact this will be very complex, as you will see soon. We can try to highlight what we have actually written. We can say these are the factors 1, and actually two basic states are not there at all. I'll also write this in blue, just to highlight. Blue is just highlighting, nothing new, just highlighting what we have actually written or commented. But there's actually also an x0 and a y1 cat and a tensor product, and an x1 and a tensor product with y0. And the products are 0 here. So this blue is just highlighting what's actually not written. Do you agree with me that or do you get what the blue part means? So from what I had written in black, I've just highlighted in blue what I had actually not written. Now, I got positive responses from you. Now, we can think about if we can write our psi cat as the tensor product of two states coming from the two subsystems or constituent systems. And any vector representing the first particle, so I'm writing this, any vector representing the first particle can be written as C0 times X0 cat plus C1 times X1 cat. So the first particle, so the first system, every particle or any vector, any state from their first system could be written like this, where we assume n and m is 2. Similarly, any vector representing the second particle could be written as something like, so we have the y0, y1, and we can say c0 prime and c1 prime. So we're not currently in the aggregate system, but we are looking at the two individual systems. Now, and that's what we've started today with. And now I just want to aggregate this. Now, we could think about to describe our psi ket, so the one from up here, through the tensor product of the two subsystems. And if that was possible, so we would have the following situation, which you will see. So psi ket as tensor product of the two subsystems. So all I had written here is we will just write this out now in a bit more detail, and then we will have a system of equations that we try to solve. So we have, what I want is the tensor product of these two generic states. So we have this generic state and this one. And we will try to build the tensor product from that now with the goal of describing our psi ket. And we will describe this now as, say, C0 times X0 ket plus C1 times X1 ket. So the first state or the first system, and the tensor product with the second generic one, which was C0 prime times Y0 plus C1 prime times Y1. And if we build the tensor product from this, what we will get is, we'll have four components because we have four basic states then. We have the X0 ket tensor product with Y0 ket. We'll have the X0 ket, the tensor product with Y1. We have the X1 ket tensor product with Y0 and the X1 tensor product with Y1. And you've learned how the tensor product works when we looked at matrices, and we saw we just multiply the individual entries with each other. So C0 with C0 ket, because we have this X0 and Y0. So we have here X0 and Y0. So this would be C0 and Z0 prime. We have the X0 and the Y1, so C0 and C1 prime. C0 and C1 prime. And the same for the others, which would be C1 and C0 prime, and C1 and C1 prime. So there's C1 and C1 prime. So this comes from C1 for X1 and C1 prime for Y1. We just sum all of this together for our linear combination. And remember, so this is now the highly generic state of this aggregate system. But what I want to describe was this one here, my entangled state. And in blue, we had highlighted what we had not written. So what I would actually want is to get this one and this one and this zero and this zero. Meaning from my generic one, I want this one as a 1, this one as a 1, but these two I want as zeros. And in order to achieve this, I would need, so I'm writing in red what I had highlighted in red, C0 and C0 prime must be the same as C1 and C1 prime, which is this and this. And I would need, in blue, my C0 times C1 prime must be the same as C1 C0 prime. And this one would be 0, and the red part would be 1. And if this was possible, then I would be able to describe this state that I had put here. But it turns out that these equations do not have a solution. So the consequence is my psi cat cannot be rewritten as a tensor product. As a tensor product. So, looks strange, right? We suddenly have a state that we cannot describe as a tensor product of the two constituent systems. Is this something that looks surprising to you? Maybe if it's surprising, send some reaction. If it's not surprising, send some other reaction. All I have shown you is also here in the slides. And I hope I don't have any typos in my iPad version. If you see any wrong character, I'm sorry, I'm trying my best. Here in the slides, it's well typed. And all I had shown you is also here in the slides for this entangled two-particle system. Now, what is entanglement? We've mentioned this term a few times. So what does entanglement mean? If we have this entangled state of the two systems and we measured the first particle, then we can see very quickly that the first particle has, because we've just have these ones and zeros, we would see that the first particle has a 50-50 chance of being found at the position x0 or x1. So after measurement, same probabilities. So what would happen if I found it in position x0? Because we have this one component here of the x0 and y0. Well, I'll switch back to this one here. No, sorry. So we have this x0 and y0. And if we find the first particle in x0 after measurement, then we know also where the second particle is, concretely in y0, because there is no component between x0 and y1. This one has been eliminated since it's 0. So if I measure the particle, or if I do a measurement only on the first particle, not the second one, and I find it in position x0, because the tensor product of x0 and y1 has a 0 coefficient, there's no chance that the second particle would be found at position y1. So if I measure the first particle in x0 I also know and measure automatically that the other particle is in position y0, because there's just no chance for it to be in y1. It's the same if I find the first particle in position x1, then this implies that the second particle must be in position y1. And this is not just a relationship in which you can infer from the one system to the other system. It also works vice versa. It's perfectly symmetrical. So if I first measured the second particle either in position 0 or 1, I would have also automatically measured the first particle because this is just a perfectly symmetrical relationship. And if this happens, then the two particles are very related to each other, and we call this that they are entangled. Not all states are entangled states. Like for example, we have a psi prime ket for which I have a 1 in each of these positions. Then, if I measure the first particle in x0, I have no information about the second particle. I would need to separately measure the second particle. But with entangled states, if I measure the first particle, the second particle gets measured automatically as well. This state here, psi prime ket, is not entangled. And there is some other terminology. So our state that is entangled is called an entangled state. And the states that are not entangled, so the states which I can build as the tensor product from states from the constituent systems, these are called separable states. So this state here is separable, while the other one we saw before is entangled. Now comes something really strange. We said we measure the first particle, and because the two systems are entangled, or it's an entangled state, the other system gets automatically measured as well. Now, theory says when you measure the one particle and it collapses, then the other one also collapses automatically or is measured. It's automatically. Even if the other particle is millions of light years away. And this happens automatically and instantaneously. So your one particle collapses into one state, then the other one automatically collapses too, and immediately, even if it's millions of light years away. Does this sound fascinating or magic to you? If so, send some reaction. A few years ago, so like 12 years ago, there was an experiment to measure how fast entanglement actually is. And it was noticed that the minimum of that speed, so to say, of entanglement was at least 10,000 times faster than light. Possibly more, but this is what that experiment determined. And Einstein once said that entanglement is spooky action at a distance. I think this comes from Einstein. Now you can wonder, could we use entanglement for high-speed communication? So communicate faster than the speed of light. From what we understand today, that does not seem to be possible. Even though they mentioned this, I don't know, in Star Trek or something, or in some other sci-fi movie or series. But at least from today's understanding, we won't be able to do high-speed communication using entanglement. But there was that experiment some 12 years ago, which shows at least 10,000 times faster than light. Now, what is entanglement useful for? It turns out entanglement plays a central role in algorithm design. For example, we have two qubits that are entangled. I measure one. the other one is measure 2. So entanglement can lead to an improved processing speed of quantum computers. Entanglement is also used in various cryptographic algorithms, as well as something called the quantum teleportation. Maybe that's something interesting for a seminar presentation. And entanglement also plays a role in relation to decoherence. Decoherence means that a quantum system loses its purity over time because it interacts with the environment. And this is something that happens in real-world quantum computers. The longer you run the computations, the more the system interacts with its environment, and the more uncertainty we add to our computations. But that's something we will see when we look more into computing. Now, talking about computing, we're now at the end of the 4th lecture. Remember, we started with the introduction and motivation of the course and saw some use cases, and we saw the quantum search algorithm, at least as an example. We discussed the math foundations. Last week, we did systems and also looked into quantum systems. And today, we've explored quantum theory or quantum mechanics in greater detail. So we saw in particular states, superpositions, a little bit observables and measurements, measuring. We saw dynamics and how to assemble quantum systems and entanglement. As of next week, we will look into computing. Concretely next week, we want to see quantum gates. So which gates can we apply to quantum states? And for that, we will use our matrix vector notation. But in order to do this, next week, we first need to see how we could describe bits and qubits. We will see how we could describe classical gates, so and or not, using our vector matrix approach. We will see some gates are reversible while others are not. Quantum gates always need to be reversible. So we see next week how we can describe qubits and quantum gates and how to build quantum circuits. And then we see something else that's called the no cloning theorem and mixed states. Because in traditional computing, you can just copy paste the variables, or you can just copy the value of a variable. That's something that does not work with quantum states. So in a quantum computer, you cannot just clone a quantum state, which comes with new consequences on algorithm design. So we will look into that chapter next week. Possibly we will not fully finish it next week. So we need 2 weeks for the architecture chapter and see how we can describe quantum computations. And once we have this, we will see algorithms, we will see quantum computers, concrete architectures, how to program them, as well as some theoretical limitations of quantum computers. I know today was not easy. Today was quite tough. As of next week, we just go down or back to 2 dimensions, 0 and 1 in a qubit, but then we will assemble a lot of qubits into more complex circuits. Are there any questions currently? If you're okay, maybe thumbs up. If there's a question, send maybe some other reaction and I'll wait for you, and you can send your question here in the chat. You should seriously revise the quantum theory we discussed today, because this stuff is not easy. Even though we switch now to computing, we still need that understanding of quantum theory, because the algorithms we'll be discussing, they work totally different than in traditional computers. And with there not being any questions, I wish you a great weekend, and I look forward to seeing you next week. Bye-bye.